Wang-Wei. I learned a lot about what you are all doing here, and we thank you for inviting us to join you. I hope we can provide something that's useful for you. It's something that we all have been working on for a long, long time, and we'd like to outline our approach to applying complexity to social systems. There it is. Whoops. How to get it working right. So we're going to, as Wang-Wei said, present in two parts. The first will be the theory, and we'll have some discussion following the talk by myself and David, and then we'll talk about applications, primarily about art cycles, but primarily about the particular work of Madeline Lennon, and then on with a very short talk about other applications that we've used. I'm going to talk about discrete systems. A discrete system consists of a collection of individuals interacting with each other more than with their environment. And what we do is we study the behavior, the state of behavior of discrete systems, particularly abstract discrete systems, to learn how they behave. And there are literally billions of those. And social systems are discrete systems, and that's the connection we want to make. Now, the interesting part of this is in the study of abstract discrete systems, there are only 4 states of behavior. They're listed here. You can think of them as solid, liquid, and gas, like those states. Often you can tell which state of behavior you're dealing with by observation. Stephen Wolfram, many people have studied discrete systems. Stephen Wolfram, in the early 80s, studying a particular discrete system called cellular automata, found these 4 states, which he called classes. Stuart Kaufman, another prominent student of discrete systems, more interested in evolutionary biology, also found these 4 states, although he calls what we list as complex here edge of chaos, but he identifies it with complexity. So these discrete systems have specific properties, and here's an example of the effect of making a small change in a social system or an abstract discrete system. And the types are very different in their way they react to a small change. Chaotic types, change spreads at a uniform rate through the whole system. At the other opposite end, order type 1, any change, if you make a change, nothing happens. And order type 2, if you make a change, it's very local, it's localized. And complex lies between chaos and order type 2. It includes some places, if you introduce a change, they permeate the whole system. And other places, if you introduce a change, it's localized. I mentioned their sensitivity to initial conditions, which is a characteristic of chaos and chaotic systems, incidentally including continuous chaotic systems. We're now talking about discrete systems. Oops, I don't know how I got there. I don't know how I got there. Just give me a second. I really don't know how I got there. Just a second. Something has happened to my machine. Let's try again.
It's complex.
It's very complex. Just give me a second, and I'll come back and do it again. It's too complex. These are what I wanted to tell you. You saw some other interesting things, I'll get there later. These are characteristics of discrete systems that it's important to identify. The first thing is very, very, very complicated systems can arise from very, very simple interactions, that is, we call rules, between individuals. And no matter how complicated you make these rules, you make them as complicated as you like, you only get the same 4 states of behavior. And not just cellular automata, but a very, very large range of discrete systems have been studied. Almost anything you can imagine. And the reason for putting this forward is that this does not depend on the particular structure of the discrete system. It's present in all discrete systems. Social systems are discrete systems. So social systems have only these four states of behavior. Now I just want to illustrate this with one that's a little more direct, and so you'll get a flavor of what we mean by an abstract system. And here's an example of a simple cellular automata. Now each row across the top, working down the page, is a time step. And if you look at the very top, there's one black cell, and think of the rest of that row as all white cells. And the color of each cell can be only two, black or white. And the color of the cell on the next time step, depends on the color of its two neighbors. That dependency is called a rule. And just as an example of a rule, it could be, if the cell is white and the cell to its left and the cell to its right is black, then on the next time step it'll be black. And you can imagine there are billions of rules, and the particular system you're studying depends on the rules that you introduce. Now the colors don't have to be just two, you can have as many as you want. The neighbors don't have to be the ones next to each other. They can be as complicated as you like. So you can make these rules very, very complicated. I'm presenting a very simple cellular automata to give you a flavor of what these look like. Now here's order type 1 example. And you can see that no matter where I put a green cell, nothing different happens. It just runs down to the bottom. So your effective change is nil. Here's a repetitive type, order type 2. And you can see the repetition. This is a very simple one. Repetitive systems, order type 2, when they use complicated rules, can have very, very, very long repetitive cycles. Now I said that very complicated discrete systems can develop from very simple rules. This is a very simple system, but it's developed this chaotic discrete system. That again, change moves throughout the whole system. It's a very complicated slide. If you said green is 1 and red is 0, and ran down the center of that, red, green, red, and so on, it's a random series. There is no shorter way to describe what we're looking at here than to show you the drawing. And finally, and the one I'm sure everybody here is interested in, is a complex system. It's a little different than the others because I started with several different green cells across the top rather than just one, so that you could see the structures here. And the interesting thing is there is an underlying pattern of permanent structure moving in that. And overlaid on that are a number of structures that, when they meet each other, as you can see many times there where they meet each other, they form new structures. Or in the language of complexity, new structures emerge. Complex systems are relatively rare. I know of no discrete system where they're more than 15%, and often they're very much less than that. The makeup of the other three depends on the system, except as rules get more complicated, order type 1 becomes less and less common. Now the cause of change between the four states, you can change them by changing the way you start externally, or you can introduce a change, like just put a new one in, and like a mutation anywhere you want. Or internally, of course, you can change the rule. David's going to talk about the parameters externally and internally that affect social systems and change their behavior among the four states that we've identified.